Okay, so I ran the Barbie bungee jump experiment, my first time running it, and that's where we tie rubber bands to Barbie, drop her from different heights, right, and with different amounts of rubber bands, and record her lowest drop distance each time. Here's my data right here. We're going to complete the table and then graph the results over here. So the rubber band distance, the unit is actually in rubber bands because you might use different rubber bands to run this yourself. But here, with 0 rubber bands, that's just her height. And the delta y, or the change, right, in drop each time is going to be 30, right, centimeters for the first one. Because if you think about what Barbie's doing, she's kind of standing on a platform. I'll draw this over here. This is some other questions we're going to answer, but I'll draw this over here for now. Barbie's standing on the platform, right? And when you have a 0 rubber band distance, she's not going to really go anywhere because she's kind of just tied at this point. You can almost imagine her just dropping upside down, right? And then what happens is Barbie's right here. So when you record that drop distance, right, that's the distance right here. This is the drop distance. For 0 rubber bands, that will be what? Well, that's just her height, right? So at 0, right, the drop distance is the height of the Barbie. That's the only one that might throw you off. So that's why with 0 rubber bands, we have her height as the measurement. So I'll clear this off, but we don't need this. I just want to explain that one. Okay, so, and then as we go along, right, we're going to find the average drop distance. So we're going to average each trial, and it's debatable here. You could say, well, I wouldn't do that. I would take, for example, the lower drop distance. In other words, I want to be really cautious. If at some point I think she reached a lower value, I want to use that value as my standard, right? Because if you can drop that far, shouldn't we consider it all the time? Well, I'm going to average them here, and again, all you do to average is add them up and divide by 2. Only common error that I see right here is people enter in 52.23 and then just press plus 48.56 and then divide by 2. But what that will do, you can see the answer is 76.51 above these two numbers because, right, what's happening? Well, the graphing calculator is dividing first using PEMDAS and then adding. So it's actually just 48.56 divided by 2 plus 52.23. So you can fix that in two ways. 52.23, put it in parentheses with the sum of 48.56, close the parentheses, and then press divide 2, and you get 50.395, right? 50.395. And another way to deal with that is, and what I usually do actually, is just add the numbers. We'll do the next line here. 79.06 plus 83.5, press enter, and then press divide by 2 in that order. And that'll give you the average, 81.28. And then as you go along, you're always finding the change in the drop. So here, if her first drop was 30 centimeters, now it's 50.395. That change is what? Well, it's a change in 20.395 centimeters. Sorry to skip ahead there. I didn't want you to watch all those calculations. But again, to find these numbers, 20.395 and 30, I'm just subtracting the change in drop distance each time, right? So for example, to get from 50.395 up to 81.28, I subtracted 50.395 from 81.28, and that gave me this drop distance right here of 30.885 and so forth. So this table is now filled out. We're going to set up our graph. Now our points, our x values, are the rubber band distances, and the y values will use our average drop distance. So if you look at our range, we go from 50 all the way up to 193. So let's set up our x-axis first. That'll be easier, right? That's our rubber band distance. And y will be the drop distance. Try to use as much as we can. So we have to go from 50, from 30, it's our height, all the way up to 193. So if I go up by tens, so what's our first point? Well, the first point is 0, 30, 10, 20, 30. That's Barbie's height. The next one is 1 and 20.3, 1 and 50.395, right? So just a little bit above 50. we're going to definitely be estimating here. And then for 2, we get a little bit above 81, right? So 81.28, so 60, 70, 80, maybe right there. For 3, we get 108.19, so almost up to 110 here. So about here. That's a 3. 4, we get almost 140. So before we had 110, so now we go 20, 30, 40, almost at 140, maybe about here. And then 166.37 for 5 rubber bands, so almost 170. This is 160 at 5 rubber bands, so maybe about here. And then at 6 rubber bands, what? 193.995. Oh, I wrote 193 up here. Sorry, that should be 190. So 190 is right here, not 193. We're going up by tens. So we go up to 193 at 6 rubber bands, so about here. And notice, it's almost a straight line, but this is not a linear function, and that's why. In the next one, they ask us to draw the line of best fit and give the equation of the line. It's not linear because the change in y is changing, right? To get a line of best fit, what we want to do is draw a line that meets or the distance where the distance from the line of the points is at a minimum. So it's not gonna cross all the points, right? But you want it to kind of be balanced so that if this point right here is below the line, then there's a corresponding point above it somewhere to almost balance it out. So I'm going to say it's certainly not here, right? That it crosses our first 2 points, but then every other point's above it. It's certainly not up here, right? Because almost all points are below the line. So it's going to be between there, right? Maybe about here because we have two points above it. We have, well, maybe a little more this way. So now we have 1 point above, 2 points below. Okay, there. All right. I'm just trying to balance it visually, right? We have this point below it, this point above it, and this point above it. So maybe I could have gone up a little bit more, but I'd say that this point is balanced out by this one, and then this point counteracts this one right there, and then the other points are on the line. So it's a fairly good line of best fit. Now to write the equation of the line, what do we do? Well, remember that one way of writing an equation of a line is to use y equals mx plus b format, right? So that just means that an equation of a line can be equal to the slope times x plus b, which is the y-intercept. The y-intercept is where your line crosses the y-axis, right here. You know that point, it's 0, 30. So b, or the y-intercept, would be equal to 30. And that's 1 point in the line. Now another point in the line, you are estimating here anyway, is use another point on the line somewhere that's friendly for you. For me, that point seems to be this one right here. And we know that point. We can't assume it crosses it exactly, but we're gonna set this up roughly, right? So what's this point right here? So again, even if it goes through it on your graph, we're using a rough approximation, right? So we don't know if we zoomed in, like, would it really be a little bit below the point, or where would it be? So anyway, we know that point. It's at 4, so 0, 1, 2, 3, 4. That point's 137.48. So let's say our line goes through what? Well, the point here would be 4, 137. So 4 and 137. So now we can find the slope of the line, right? How do we do that? Well, we find delta y, that's the change in the height between these 2 points, subtract the y values, so that's 137 minus 30 over delta x, 4 minus 0. So that equals what? Well, 107 over 4. 107 over 4, well, 4 goes into 125 times, and then once more before it hits 107, so that's 26, with a remainder of 3 or 3/4. So our slope is 26 and 3/4 x, right? Y equals 26 and 3/4 x plus b, and b is 30, so we have that. So there's our equation of our line. Now, eyeballing it, that's our rough approximation of a line of best fit. Now we go further in this investigation here. And what do we do next? Well, they want us to find the average slope and graph of this line. Include the equation for the line and state whether or not this line is a good fit for the data. If it is not a good fit, adjust the equation to make it a good fit. So by average slope, they just mean average the changes or the delta y's that you have right here. It's these numbers. So we just add them up and divide by the number of numbers that we have, right? So that's what? 30 plus 20.395. So our average slope here is 27.71357,143. All right, well, I'm just going to round that to 27.7. So we'll go back over here. And that's pretty interesting, I think, because that means it's really close to the slope we just got right there. So in this one, it's equal to 27.7. Right? We had 26.75, so it's only one away, almost about a little bit less than one away. X plus, well, let's put it through the y-intercept and see how it looks. So that's our equation for the average slope. How do we plot that? Well, we have the same y-intercept, this point right here, and this slope, 27.7, what does that mean? Well, slope is equal to delta y over delta x, or change in y over change in x. So that means if I start at any point and my slope is 27.7, I can think of that as going up on the y-axis 27.7. And since 27.7 over 1 is the same number, we can think of it as up 27.7 and over 1. So now I'm just going to do this on my graph, right? I go up 28, 10, 28, and over 1. So for me, 1 is all the way this distance right here. So it's a point about here, right? In fact, probably even a little bit lower. So 27.7, 28 right there. See how close it is to that point. And do it again. Go up 10, 28, and then over 1. And you can see that essentially you really only need 2 points to graph a line, but I went for 3, right? But these lines are very close, right? So my visual approximation is very close to this average slope line. So on this scale, these lines are almost identical. They're hard to distinguish. So we have the two lines. And now what do we do next? And oh, by the way, I'm not going to adjust this line, the orange line. I think it's a really good fit, maybe even better than mine, because yes, we have these 2 points down here, but it goes through this point and this point almost exactly, and this one, and that one. So it seems balanced as well. So instinctively, I'm not sure which one is a better fit. All right, we're just going through some learning. All right, now we're going to find the line of best fit and graph it. Okay, so we're going to do this on a graphing calculator, but I'll show some software that can do this as well. So to set up the line of best fit, we want to go into our list. I press second stat, and my lists are over here. If you already had them entered, you could do it that way, but what we'll do is just press. So now we want to find the line of best fit, and we want to do that with the linear regression formula, which can be utilized in the graphing calculator and other software as well. We'll look at a little bit of each. But here on the graphing calculator, just press stat, clear the list that you want to use. I'm going to use list 1 and list 2, so I hit second 1 for list 1, comma, second 2 for list 2, and now my lists are cleared. Under stat, you hit edit, or the first option, and now we're going to enter in our x and y values. The x values are just the 0, 1, 2, 3, 4, 5, and 6, the rubber band values, and then the second list will be our y values, or the drop distances here that we've already recorded. So I'm going to use the average drop distances here, so that's 50.395. For list 2, we're going to enter in the drop distances, so 30 at 0 rubber bands, and then 50.395. All right, that's for 1 rubber band, 81.28, and then 108.19, and then 137.48, right? 166.37, and 193.995. Now, 995, 193, sorry, 0.995. So now these points are entered, you want to make sure that you're able to set up a stat plot. So you hit second y equals, I'm going to use plot 1. You can use any of these, but plot 1's first, so I'll check that. Plot 1 is on, good, that's what I want. I want it to be on the scatter plot right here, and I want it to use list 1 and list 2. So that's all set up. Now you go to zoom, and the ninth option is zoom stat. I'm just going to press 9 to select it. Now you can see the scatter plot, the points that we have from the Barbie Bungee. Now to get the line of best fit, all we have to do is hit stat, go to calculations. We want to find linear regression, that's choice 4. We want to find it for list 1 and list 2, what we just entered, right? Those points. So list 1, comma, right, list 2. Alright, so treat them as points. Hit enter, and we've got it. Here's our line of best fit. So these two numbers here, a and b, you see they write the equations, y equals ax plus b. Well, that means that a is our slope and b is our y-intercept. So over here, if we just, right, set it over here, move this, and enlarge it a bit. Okay, so these numbers, of course, are different from what we got before, but they're remarkably close. I mean, here, the average slope, 27.7, is very close to this right here, 27.86. Our eyeballing it is a little bit further, 26.75 or 26 3/4, but it's still pretty close. What is different here is the y-intercept. They lowered the line. So I should have lowered the orange line to make it a little bit more accurate, right? Because this is the line of best fit here. And the equation would be y equals 27.86453571 plus what? The b value, right? The y-intercept 26.07410714. So we'd plot this here. We're going to have to set it up as like a rough estimate. So as we draw this one, I mean, keep in mind we are estimating, but we want to try to be as accurate as possible. So with b, it's a 26, right? So it's lower than our other points right there. We want to set up our y-intercept right there, and then we go up almost 28, but then over 1, our slope, because our slope is almost 28 over 1. So we go up 10, 20, right, and then 8 and over 1. So it's right here, and let's do it again, 10, right, 28 and over 1, so here. And this line's interesting because, you know, as we said, this line of best fit up, what happens is it kind of sandwiches between the two lines we have already, right? So that's our actual line of best fit, and to reach that, they had to lower the y-intercept. Now, you can really only understand these differences, I think, if you have a better scale or if you use some software to graph it. Here's a GeoGebra. We've graphed our 3 lines, right? This is our line of best fit. The visual guess is right here, very close, but you can see the gap between them starts to widen over here, and that will become more dramatic over time. And then the orange line, the average slope, right, it's kind of, I guess, if you see it right here, it's above the other line, so that's the line of best fit is sandwiched between them. Oops, fix that. And what I mean by using software here is just that, you know, if you zoom in, you can see that, yeah, all these lines are indeed actually different, because on this scale right here, right, you can constantly see the gaps between the lines and the points. It's hard to see with our graph because the scale isn't high enough. So it's just one thing to keep in mind. I don't think it's important to set up this crazy scale to see the difference, but it is nice to know how to graph them by hand and then to see those intricate details with the software. And also you could calculate your line of best fit. If you don't have a graphing calculator, click Our Class on shaunteaches, scroll down to the playground, and then all the way down to GeoGebra. And here what I tried to set up were different worksheets that should work really nice with the Barbie Bungee. Depending if you had 4, 5, or 6 trials, there's different calculators here for you. So let me just wait a second while it loads. Okay, here it is. So if you had 6 trials, right, all you have to do is type in your values right here. Let's say your first value is 30, and then 55, and then 77, and then 118, and so forth. What it will do is it'll graph and calculate your line of best fit for you. If you had 5, up to 5 rubber bands, you would use this chart right here. Just type these in, and 4 rubber bands right here, 4 rubber band trials on top of just the 0. Then you can use this one, and then this is just customizable if you had just 3 data points. But so these calculators will automatically graph and calculate your line of best fit. Alright, so now the last thing, and we're almost there, believe it or not, is to use these lines of best fit to make some calculations, right? If we were sending Barbie on a 200 centimeter jump, how many rubber bands would we need? And base your answer on each of the lines from B, C, and D, and then compare absolute and relative error. And then we're going to look at 2,000 centimeters and do the same thing, and look at the absolute and relative error. So first let's calculate, and then we'll talk about the relative and absolute error. Okay, so we've got our formulas here, and we'll start with our visual guess. And if Barbie's jump is 200 centimeters, that means y is 200. We plug that into our formula, so it becomes 200 equals 26.75 x plus 30, right? We're solving for x, so solving for the rubber band. Subtract 30 from both sides, that would give us 170 equals 26.75x, but I'm going to divide both sides by 26.75, and then x is equal to 170 divided by 26.75, which is about 6.355. So 6.355 rubber bands. Now yes, I know you can't have a 0.355 of a rubber band, but over a larger scale these decimals will matter, and here we want to at least see that there is a difference between these formulas. The same thing here in our next one, which is used our average, or 27.7. So now it's 200 equals 27.7x plus 30. Subtract 30 from both sides, and then divide by our slope, or 27.7, and that gives us our x value. And this is going to equal what? Well, let's go over here. We've got 6.137, so a little bit less, right? 6.137, because our slope is greater. It's going to give a little bit less of a value, right? Because the rate is increasing faster. So that means 6.137 rubber bands will bring you the same distance. In our line of best fit, let's see what happens here, right? So now it's this formula is a little bit, right, tedious to write, but we can handle it. 27.86, so forth, right? I'll use the full decimal, x plus 26.07, and so forth. We'll use the whole thing. So it becomes, again, following the same formula, we'll end up doing 170 divided by 27.86, and so forth, and that equals x. So let's see what this is. So this slope is the greatest of all three, right? So this means the number we'll get will be the least. So let's set this up. So it's 170 divided by 27.86. Wasn't entering. Start over. Okay. Oh boy. So it's 170 divided by 27.86453571. Hit enter. 6.10, and then I round it up. The 9 rounds up the 0 to a 1, so 6.101, and that's our number of rubber bands. Now, what's the relative error, or here an absolute error? Well, here we're treating this as the actual measurement, and we're treating these as the measured based on visual or averages. And absolute error is just the difference between your actual and your observed, or in this case, guessed, visual guess, or average values. So absolute value, you just subtract how far off are you from the actual, right? So here, the absolute error for the average slope one will be 6.137, right? 6.137, right over here, minus 6.101, and that's only what? Well, 6 and 3, it's 0.036 off. That's our absolute error, all right, AE. Now, the relative error for that one is as a percentage out of the actual amount. So it's 0.036 over, a relative is like a ratio, out of the total, 0.101. This is your relative error, and that's 0.036 divided by 6.101. It's a very small number, 0.0059, we'll say. 0.0059. That just means, and that makes sense, right? Because these numbers are so close together that in comparison to 6.101, a 0.036 in error almost means nothing. And in the other one, our visual was also very close. So that would be what? We have 6.355 minus 6.101, and that's 452. It's a bigger error, 0.254, and let's see what that is in terms of relative error. It's 0.254 over 6.101. This is our relative error now. So it's 0.254 divided by 6.1101. So it's 0.04, or about a 4% error. 0.041, we'll go the same decimals, 4 places, 6, right? Yeah. So yeah, it's a much bigger error than it's much further off than the other one, which we observed before. But still, the relative error doesn't matter that much. So on a small scale, the relative error is tiny. In fact, it's not even a full rubber band away. But over 2,000 centimeters, these things will matter a lot more. But that's something I want you to reflect upon and think about and calculate on your own. I just want to help you get started on this project to kind of think about how these numbers are changing your results over time. Thanks.